To initiate a turn, birds mostly use asymmetric wing-morphing control techniques to roll their bodies and thus redirect the lift vector to the direction of the turn. However, when soaring, raptors can execute slow and steady banked turns without any observable wing movement, other than twists of the tail. Although tail twisting can compensate for adverse yaw, how raptors use only tail twist to perform banked turns is not well understood. To study the avian turning maneuvers, we developed a raptor-inspired drone, featuring morphing wings and tail covered by feather-like structures. We designed the drone using a bio-informed design approach, considering not only similar structure, geometry, and morphology of a hawk, but also its inertial and aerodynamic parameters. We characterized the aerodynamics of the drone using a force sensor, mounted at the tip of a robotic arm positioned in front of the open wind tunnel, and a real-time flow visualization and measurement system. We found that when twisted, the tail, located very close to the wing trailing edges, enters asymmetric flow regions induced by the wings. This results in the generation of asymmetric lifts on the two sides of the tail, therefore producing both roll and yaw moments to coordinate a turn. An experiment on a single degree of freedom gimbal showed that twisting the tail initiates rolling motion of the drone. Indoor flight experiments also validated that tail twist generates sufficient control moments to initiate, regulate, and end banked turns in our feathered morphing drone, and also in a fixed-wing drone. We observed that birds also use tail twisting during high-speed sharp turns. In this maneuver, the bird coordinates tail twisting with a rapid pitch-up motion when entering the turn, and employs asymmetric wing morphing to effectively exit the turn. We reproduced the high-speed flight maneuver using the morphing drone. To initiate the pitch-up maneuver, the tail was deflected upward. During the climb, tail twist was applied to induce roll and yaw movements. To exit the turn, the drone reversed the tail twist and applied wing shape morphing to recover level flight. We showed that the pitch-up maneuver enabled by tail twist and pitch substantially reduced flight speed, allowing the drone to perform sharp 90 degrees turn. Also, wing morphing enabled fast level flight recovery from the agile turning maneuvers. Our findings help better understanding of avian flight behaviors, and bring us a step closer to the design and control of a new generation of drones that can fly more like birds.